Start again. Okay, and we're going to start talking about series. What is a series? What do you remember? What's the difference between a sequence and a series? Really? Okay, a series is just the sum of terms in a sequence. A series is the sum of terms in a sequence. We're going to add up numbers in a pattern. One example of a series, 1 plus 4 plus 7 plus 10 plus 13. Now, is this looking familiar? Go evaluate that series. What do you got? 35. It is. The most straightforward way to write out a series is just to do exactly what I did, show the entire sum. Now, you're not going to have too many problems like that because I know you know how to add. Next couple classes, we're going to look at sums written in a form like this: 1 plus 4 plus 7 plus 10 plus 13 plus ... S sub 72. What does that mean? What do you remember? Connor?
Add all of them until it kind of gets 72.
Yeah, you're going to add up 72 numbers. That's exactly what this is saying. The sum of the first 72 numbers of the sequence, or 72 terms of the sequence. We'll deal with that next two classes when we talk about arithmetic series and geometric series. But there's another way to show series. Do you remember something involving a Greek letter from last year? Sigma notation. That's what we need to look at. And that's really what we're going to deal with for the rest of today. Are you going to be like my freshman with that? Yes. All year there's skippity sigma this and oh my, I still don't know what it means. Yep, wonderful. Often written, and I try to explain to them that word means it's a sum, you're adding things up, and they tell me I'm wrong. Often written in what we call sigma notation. Does it actually mean anything? The way they use it? I can't get a straight answer from anyone. You're not helping.
They're saying it like it means cool.
Yeah.
So what does skippity sigma mean?
It's like silly. It's like silly cool.
So if I ask you solve this equation, they're telling me it's silly. Never mind. Oh, wonderful. They're,
Yeah. Skibbity used as like a silly or joke like, and then Sigma's used as like cool.
So the sigma, the sigma, I think the definition now.
Someone could be a sigma.
okay, so we're going to use it as a symbol that means the sum. Try to learn new things every day. Greek letter like that. I'm going to say I equals 1 to n of a sub I. A1 plus A2 plus A3 plus ... plus A sub n is what this means. The I equals 1, I'm going to call my lower limit. The n, I'm going to call my upper limit. That Greek letter sigma just means sum. Did you guys do like some statistic stuff earlier in the year, like standard deviation? Does that sound familiar? Okay, if you take statistics next year, you'll see that there are sigmas in those formulas, basically just to show, add up a whole bunch of things. A sub I is our sequence formula, the formula that gives us our pattern of numbers. My lower limit is the first number I'm going to plug in, so I want to find A sub 1. And then I'm going to keep plugging in numbers until I reach that upper limit, until I reach A sub n. Let's do a few of these. Let's look at the sum as I goes from 1 to 6 of I squared plus 1. We are going to get into some shortcuts for dealing with these things, but for this first problem, I want to do it truly by writing out all the terms and then just adding them up. So I have my sequence formula over here, I squared plus 1. I'm first going to plug in my lower limit. I'm going to plug in 1. And I'm going to get the problem 1 squared plus 1. I'll do it in a moment. I'm then going to add. Well, you're going to plug in 2. 2 squared plus 1. Then what? Plug in 3. 3 squared plus 1. You're going to keep doing this until you plug in what? 6. 6 squared plus 1 will be that last term. And I know it's the last term because 6 is my upper limit. Keep going. Do each set of parentheses, add them up, and let's get our sum. I think calculators are fine with this. I think most of your tests, if not all the tests, will be calculator. But that does also mean I definitely have to see this work. Show me how you're plugging in, and then just add them up on calculator. Answer is? It is. Let's do a slightly harder one. Let's deal with the sum as I, no, let's not do I, let's change the letter. As k goes from 4 to 7 of negative 2 to the k minus 5. What are you going to plug in first? 4. Plug in 4, plug in 5, plug in 6, plug in 7. And then add things up. See what you can do. Write out those terms, show the plugging in step, show the simplified step, give me a sum. I believe it's going to be a nice round number, albeit negative. Emily, do you have an answer for this one? It is. One more like this. Let's do the sum as j goes from 1 to 5 of 4. Huh? What is this saying? When you plug in your lower limit to your formula, hello. When you plug your lower limit into your formula, what do you get? 4. Okay, I just plugged in 1. Plug in 2. What do you got? Plug in 3. What do you get? You see where this is going. How many 4s are you going to end up with? 5 of them. I'm going to plug in 4. I'm going to plug in 5. They all give you 4s. You should get 20 for that sum. Anything here? One thing that we're now really going to spend the rest of the period dealing with, I don't think these are too bad, but could you see that like this first one would be really horrible if I wanted you to do the sum as I goes from 1 to like 252? There's got to be better ways to deal with that. And that's what we're going to start dealing with now. I've got 2 properties and then 4 shortcut formulas that we can use to evaluate special types of sums. Oh, you know what? I take that back. Before we do that, we've got to talk about writing series in sigma notation, which is definitely a skill you'll need for next year. Write each series in sigma notation. For example, 1 to the 5th plus 2 to the 5th plus 3 to the 5th plus 4 to the 5th plus, I'm going to go on for a really long time, I'm going to end with 13 to the 5th. I want to write this thing in sigma notation. And the trick is I'm going to look for what's changing. I think every single term has a 5th in it. That's not changing. What is changing is the thing that you're raising to the 5th. I want to put a little note over here and say, look for what is changing. And what's changing, I'm going to either make that my variable or make it based on my variable. Let's make our variable I. What do you want to go from and go to? Like, what number would you plug in first? What number would you plug in last? There are a bunch of ways to do it, but I think the easiest way is going to be to go from I equals 1 to 13. Now, inside the sigma, what would you get inside your sigma if I want to express this sum? Don't overthink. I to the 5th. The only thing changing is what we're raising to our 5th power. So I'm going to say sum is I goes from 1 to 13 of I to the 5th. Next one. Let's do 2/3 plus 3/4 plus 4/5 plus ... plus 13 over 14. I see, again, several ways to do it, but I see 2 that are going to be a lot easier than other ways.
Pretty distracting.
Yeah.
Yeah.
I'm just going to do math right now.
I agree.
Let's make I the variable. Thoughts on the limits? 3 to 14, that'll work. What else could work? 2 to 13 would work. I think those are probably the two best options. How about I first do 2 to 13, and then I'll try to do it 3 to 14, and they should, in the end, mean the same thing, even though they're going to look a little bit different. I'm going to go 2 to 13 first. Your top is 2, 3, 4. I think the top is just I. Formula for the bottom. I plus 1. Or we could do the sum as I goes from 3 to 14. See if you can write out that version. If you're going 3 to 14, what's the top? I minus 1. And the bottom is I. Could you see any other way of doing this?
You could do like a really big number and then do like I minus like 15.
So like I goes from 17 to, okay, let's start doing this. Maybe 17 to 28 of I over 17 over what? What's the bottom going to be? I minus 14, something like that. I don't think that would be like an obvious way to do it, nor a useful way. But any of these would work. There are really infinitely many ways to go about doing these things. I think go with the top couple. Okay, let me give you one more about as tough as they can get. And formulas like what I'm about to show you are used quite a bit in calculus when we try to find the area under a curve. Let's do 1/10 times the cube root of 2 plus 1/10 plus 1/10 times the cube root of 2 plus 2/10 plus 1/10 times the cube root of 2 plus 3/10 plus ... 1/10 times the cube root of 2 plus 50/10. Can you please go write that in sigma notation? By the way, those of you who just came in, I'm recording stuff. I'll get the videos up later so you can kind of see the whole story. Again, look for what's changing. Anything not changing is just going to be a constant inside your sigma notation. Again, infinitely many ways to do it, but I think the easiest way is to say I goes from 1 to 50. Every term has a 1/10. I need that. Every term has a cube root. Every term has a 2. The only thing changing is the numerator of your fraction. So I think it's going to look like that. Anything here? Okay, now what I started mentioning earlier. If we want to try to do like one of these sums, I goes from 1 to 100, that's going to be a pain. We don't actually want to write out all 100 terms. There are some shortcuts that we can use, 2 properties and then 4 formulas that we can use to do this easier. So this next piece, properties of sigma notation and special sums. And special sums. 2 properties. First one is our constant multiplier property that says if I want to do the sum as I goes from 1 to n, of some constant times a sub I. I can take that constant out front before my sigma and say C times the sum as I goes from 1 to n of a sub I. And Emma, like I said yesterday, I've been recording things. I'll get these up because you'll want to hear the beginning of the story. For example, if I want to do the sum as I goes from 1 to 17 of 2I, I could do this by just doing 2 times the sum as I goes from 1 to 17 of I. I can add up 1 plus 2 plus 3 plus 4 up to 17 and multiply the answer by 2. And in a moment, we'll see a shortcut way for doing 1 plus 2 plus 3 plus 4 up to 17 without having to write them all out. Second property is our sum and difference property. If I have two different sequence formulas inside my sigma, I can split this into the sum, or difference, of two different sigmas. I can add up the a sub I terms, plus or minus. I can add up the b sub I terms. For example, the sum as I goes from 1 to, I think I'm just going to say n over here, of I squared minus I. 1 squared minus 1, plus 2 squared minus 1, plus 2 squared minus 2, plus 3 squared minus 3, plus 4 squared minus 4. Rather than doing that problem, I can do the sum as I goes from 1 to n of I squared minus the sum as I goes from 1 to n of I. I can do 1 squared plus 2 squared plus 3 squared plus 4 squared minus 1 plus 2 plus 3 plus 4, which again will be an easier problem. Therefore, still going, Daniel? You're okay. There are 4 special sums that we're going to need to be able to work with. And I am fairly certain this is not something that you dealt with last year. First one, the sum as I goes from 1 to n of C, of just a constant. This is like asking you, what's our constant? Plus our constant, plus our constant, plus you're going to add up a whole bunch of those constants. How many of those constants do you have? N. This is sort of like that problem where I had you do the sum as I goes from 1 to 5 of like 4 or something like that, where you did 4 plus 4 plus. What is this sum? N times C. I'm going to switch the order, doesn't really matter. C times N. The second sum. The sum as I goes from 1 to n of I, which is like asking you, what's 1 plus 2 plus 3 plus 4 plus, you're going to go on for a really long time, and eventually you'll add up n. And I feel like you probably heard a story about this last year. Anyone remember the name Gauss, a mathematician? He was really good at math, even when he was just like a little kid, which was a little bit annoying for his teacher because, well, I mean, he was so far above everyone else and bored, and one day, she said to try to keep him quiet for like a little bit of time so she could work with the other students, I want you to go sit down and add up 1 plus 2 plus 3 plus 4 plus 5 up to 100. And he sat down and came up with the answer in about 30 seconds. 1 plus 2 plus 3, plus 4, plus 97, plus 98, plus 99, plus 100. Do you remember the story from last year? What did he do? Let me tell you what he didn't do. He didn't do 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. That's what the teacher wanted, because that really would keep him busy for a while. What's 1 plus 100? 101. What's 2 plus 99? Okay, what's 3 plus 98? They're all 101. How many of these pairs are we making? 50. You're going to do 101 times 50, and you're going to get 50-50. In general, if we want to add up 1 plus 2 plus 3 up to anything, all I have to do is add up my first number and my last number. Okay, n plus 1. First number plus the last number. That's where I'm getting my 101 from. Then I need to multiply by the number of pairs. If there are n terms, how many pairs can you make? Divide by 2 times n over 2. This isn't really the standard way of writing it. The standard way of writing it is n plus 1 divided by 2. We'll use this formula in just a moment. Number 3. If I want to do the sum as I goes from 1 to n of I squared, which is like asking you what's 1 squared plus 2 squared plus 3 squared up to n squared. I don't have a great story for this one. It's just a formula that can be proven using some mathematical logic. It's n plus 1, 2n plus 1, divided by 6. And our fourth formula, the sum as I goes from 1 to n of I cubed is going to be n squared times n plus 1 squared over 4. And what I want to do now is use our properties of sigma notation along with these special sums to try to figure out this thing, which would be an absolute pain to do by hand. Plug in 1, plug in 2, plug in 3, plug in 4, plug in up to 41. That would take you a long time. Our formulas can help us get there faster. So we're going to go do the sum as I goes from 1 to 41 of 3i squared plus 4i plus 1. Step number 1. I can write this as 3 separate sums. I can say that this equals the sum as I goes from 1 to 41 of 3i squared plus the sum as I goes from 1 to 41 of 4i plus the sum, as I goes from 1 to 41 of 1. And same thing I said yesterday, I've been recording stuff. I think both of you are here tomorrow, so you'll spend tomorrow. Bring in headphones, you'll watch things. That was step number 1. Step number 2, I'm going to use my constant multiple property. I'm going to take that 3 and that 4, I'm going to move those out front before my sigmas. I'm going to get 3 times the sum as I goes from 1 to 41 of I squared plus 4 times the sum as I goes from 1 to 41 of I plus the sum as I goes from 1 to 41 of just 1. This question is asking you what's 1 squared plus 2 squared plus 3 squared plus 4 squared up to 41 squared. Well, I have a formula that will do that. That was that third formula over here, the sum of 1 plus 2 plus 3 up to n squared. To evaluate that first sum, you're going to do 3 times. Plugging into my formula, what's n for this first problem? 41. You're going to do 41 times n plus 1, so that's 42, times 2 times 41 plus 1, that is 82 plus 1, I think 83, divided by 6. Next, 4 times the sum as I goes from 1 to 41 of I. 1 plus 2 plus 3 plus 4 up to 41. Again, we have a formula for that. This formula over here. I'm going to do 41 times 42 divided by 2. By the way, these 4 formulas are not formulas you will have to memorize. I forgot to get out my poster that I normally hang on the board at this point with the 4 formulas, but on tests and stuff, you will have them written right on your test in front of you. All I care about is can you use them. Same deal next year in calculus. Don't have to memorize those. The last one. I want to add up 1 plus 1 plus 1 plus 1 41 times. Well, I think you know how to do that, but if you just want to use the formula, that is our top formula over here. I'm going to do my constant of 1 times the number of terms times 41. Go to your calculator and work through that calculation. Then I want to do one last problem, and then we'll be good for today. I think it's 71463 plus 3444 plus 41, I believe. I think. Who's got something?
7494.
That's what I got. I want to do one last problem like this. Am I correct? This is not stuff you dealt with last year. Okay, finally, something new in here. Okay. I want to go do the sum. As I goes from 1 to 10 of I times I minus 4 squared. We can only use our properties and use our special formulas if we're in like standard form. Nothing factored, nothing undistributed. What you have to do first here, expand this thing. Foil that thing out and distribute the I. Let's put it in a form just like that last problem, that 3i squared plus 4i plus 1. Take 2 seconds and go do some algebra on the stuff inside. While you are foiling stuff, I'm going to get the homework out. If you are here tomorrow and we're here the entire period, don't do the homework tonight. Just do it in class tomorrow. If you were not here today but will be here tomorrow, don't bother with this. Tomorrow in class, you're going to watch the video, then you're going to start working on things. And if you weren't really here today and won't really be here tomorrow, you'll work on these things on your own. Yep. Also, please remember, cumulative review due Friday. Get that in tomorrow. If you're here tomorrow and we're here today, you can also use tomorrow's time to just work on the cumulative review. But I'll need them by Friday, and we don't have class, which means you're going to stop by. Let's see. I times I squared minus 8i plus 16. I think this will become, the sum is I goes from 1 to 10 of I cubed minus 8i squared plus 16i. Do you see where I'm getting that from? The rest of this now is just a matter of using the properties and then using our sums. I goes from 1 to 10 of I cubed minus 8 times the sum as I goes from 1 to 10 of I squared plus 16 times the sum as I goes from 1 to 10 of I. Then you would you'd use your formulas, you'd add up your answers. And I think we're going to stop there.